So now we'll go ahead and do an example of a glue lamp beam. We're going to assume it's a 24F-1.8E. Remember, that's the mechanically graded glue lamp. It's dry service, normal temperature, deflection criteria from IBC, for roof beam supporting a non-plaster ceiling. Remember, we have some tables for that. We'll go through this. The compression face is laterally braced at 8 feet on center. So compression face, the top face is braced at 8 foot on center. Dead load is already got an allowance of 100 pounds per linear foot for self weight. So if we go over that, we'll have to adjust. But for our first pass, we're going to assume then 250 pounds per linear foot, and that would include the self weight, then a snow load of 750 pounds per linear foot. So we're going to do the usual flexure, shear, and deflection, but this time we're going to use a glue lamp member. Oops. All right, so let's get started on this one. Glue lamp. Flexure example. And we'll look at the shear and deflection. All right, so our demand W, or we call it W total load or whatever you want to call it, is WD plus W snow, and it was 250 pounds per linear foot plus 750 pounds per linear foot for a nice round 1,000 pounds per linear foot. Moment, the good old WL squared over 8. It's all uniform load, and it is a simply supported beam. So we'll get 1,000 pounds per linear foot. It's a 48-foot span. So it's a long span compared to what we've been doing. Squared over 8. And we get 288 kip feet. Okay, we've been playing with pound feet in the sawn lumber, but now we're talking about a much longer span. This glue lamp is going to be a bunch of lumber pieces laminated together, and so we're now in kip feet. So this is looking more like some of the structural design you've done with other materials. Okay, so about X bending would be M over the S sub X. But we don't know S sub X. We got to choose the member size first. Right, that's the design problem here. All right, so we know that we have to be less than what's required. So we're going to solve for S sub X, just like we did on the design sawn lumber problem. And now we'll follow the same process we've been following, but now we're going to look at, so in glue lamps, we're going to have this X piece because that designates which way the laminates are going, which way we're bending. Same idea as before, but now we have to go to table 5.3.1. 5.3.1 of the NDS code to find what are C values we use for glue lamps here. In flexure, CD, CM, CT, CL, CV, CFU, C sub C, and C sub I. I missed one here. Yeah, C sub I. All right, so if we go and look at this, I'm just going to switch up colors here. We're going to look up FBS in the table. A lot of these we've done before. So in this case, we go through this. C sub D is 1.15. CM is 1. CT, the temperature one, is 1. I don't know C sub L. I don't know C sub V. And remember these two, if you go look in the table, table 5.3.1, there's a footnote that says we don't apply those simultaneously. So we use the smaller of the two. So we're going to have to figure out what those are and then use the smaller one. F sub fu 1, C sub c 1, C sub I 1. All right, so what were the new ones here? Well, the ones we're going to have to deal with are C sub v, which is the volume factor. And we have the C sub c, which is a curvature factor. We're not starting out looking at curvature in this beam at all, so that's 1. C sub I is a stress interaction factor for tapering. Stress. And this means that when they make the thing, it's got a taper to it. So we're not doing anything fancy with tapering here, so that one's also 1. All right. So what we got to deal with is C sub L, which is the lateral stability one, and C sub V. So we use the smaller of those two guys, the lesser of those two. So how do we do this? Well, we don't know either one of them. And this is not as straightforward because when the saw and lumber chapter, there's that 4.4.1 section that allows us to use some rules of thumb. This wasn't a case where it's continuously braced, so we don't have that out. So we've got the 8-foot on-center bracing, and we're going to have to figure out what is C sub L, and we don't know what C sub V is either because that is a volume factor, and that means we have to know what the size of the thing is. So if you go in on page 37 or section 5.3.6, the volume factor is an equation, but we don't know what the member size is yet. So page 37 or 5.3.6 of the NDS has your volume factor. And that equation is C sub V equals 21 over L, the length, times 12 over 1 to the x, times 12 over d, 1 to the 1 over x. Sorry, I said that wrong the first time. And then 5.125 over b, the 1 over x. So kind of messy, but nothing, not a hard equation. And the max that you can use there is 1.0. In our case, x is 10, so x is 20 if it's Southern Pine, and it didn't specify we had Southern Pine here today for this example. Any other wood is 10. Okay, so we could make up a size. If we'd been doing a ton of glulam design in our office, we would probably have a really good idea where to start with this. My gut feel would be something around 0.8, but I went through this problem and it might look too suspicious because the actual answer I came up with was pretty close to 0.8. So we're going to use just a guess of C sub V based on if you happen to have the wood book or have access to it, they do a similar problem here. And they just say, guess 0.82. Okay. Now, there's no description of why I guess 0.82. Typically, you'd have a feel for this. I would say you could throw in a dimension and see what you guess. There's no good reason here that I'm guessing 0.82, other than that was the guess that was used in the example problem in the book. You could use anything. I would say keep it between 0.75 and 0.1. It's probably a good start. So, and 0.8 sounded like something good to me. Anyway, it'll also, this will depend. You may choose a different section size than I do because there's several section sizes that are pretty good once we look in the glue lamp tables for this one. So let's just say we're going to guess this and move forward, knowing that it's just a guess and we can do whatever we want. So we're going to use the lesser of these two. Let's just use this and assume it's the lesser for now until we can figure out what these two guys are. And it's pretty hard to guess Cecibel, so this is as good as it's going to get for now. All right, let's go back and find our equation. So f sub bx up here, we can look that one up. That is in the supplement on page 54. Page 54 will give you the section tables in that area. F sub bx. So pause this video and go look the things up that I write in red to make sure you see where it's coming from so it's not totally confusing. If you've got a hard copy of the NDS, I would go ahead and put your sticky tabs or whatever you want in there so that you can find this stuff easily. Okay. If I look this up, I can, for the glue lamp beam that I was given, which was a 24F-1.8E, we know the 24F means it's 2400 psi, so I don't actually have to look that part up. But you can, and it'll show you in the table that that's what it is. Okay, let's go ahead and put in all the different C factors and get an answer here. So 1.15, 1, 1. We don't know yet what C sub some of the other ones are. Let's put in this with 0.82. You remember when we were up here, basically everything is 1. We had a 1.5 here, and then we had our other guys. And, well, the last three were also 1s. All right. You don't have to put all the 1s in for your calculations. It does help to do that just as a double check so you don't drop one accidentally, especially if you're doing a problem with wood on, say, your licensing exam. That's where you will miss points. And so make sure that you're catching all those C values. It's very, very easy to miss one of those. So we need to solve or find our little f sub b. 288 hip feet is the moment. 12 inches per foot. I need 1,000 pounds per kip. And then I have S sub x. And the F sub B stress that I'll get here is, sorry, needed to write this down. I was talking so much, I forgot to write down. 2263 psi is what we got for the F prime sub Bx times the C values. Sorry, F sub Bx. There we go. All right, so we're going to take that equal to 2263. All right, so our stress equals moment over Sx so that we can find S sub x. Okay, so solve for S sub x and we get 1527 inches to the third. Now remember, this is just an estimate at this point because we assumed a CV value, and we haven't even found a C sub L value yet because we have to see where we get for section size and then check all those things. So go to, at this point, go to table 1C, which are the section properties for the glue lamps, and take a look at a couple sections. So I'm just going to pull a couple out that would be at least 1527 for an SX value. One is a 6 3/4 by 37.5, and that will give me an S value of 1582. There's a 8 3/4 by 33, and that one gives me 1588. This one's 10 3/4, another one's 10 3/4 by 30, and that one gives me 1613 inches to the third. Now, generally, I've got a little wiggle room here. I would try to get the lightest one. In this case, that's this one. It's not lightest because the S sub x is lightest, although that's true in this case too. It has the smallest area. So the area of these, I think, areas, this one's about 253, this one's about 289, and this one was about 323-ish. So the smallest one, right? Because I can get S is I over Y. And remember, if I had depending on my shape and how far stuff is from the neutral axis, I could have an I value that's bigger with a smaller area. Now, I just put this over here to remind you that's what is going on. These are all rectangular sections, so as long as I'm using the same kind of, basically the same kind of wood through the laminates, I would probably just go with the smallest x value, or S sub x value in this case. Okay, doesn't really matter. Use one of the ones. We're gonna use this guy. So if I try a 6 3/4 by 37.5 Goulam. And now we need to find actual C sub V, C sub L, and figure out which one's the smaller to control. Then we're going to be able to check flexure. All right, so C sub V, we're going to use that equation now. 21, L is 48 over 1/10, or to the 1/10, 12 over 37.5 to the 1/10. And 5.125, so this is the formula from the previous page, over 6.75. So now I have the dimensions to put in here, okay? And I get 0.799, which I always hated if a professor did their guess and the guess worked out perfectly the first time. So since we guessed 8.2 or 0.82 instead of 0.8, our guess wasn't perfect, but it's pretty close. So we will call our CV value here 0.80. But we don't necessarily know that that one controls, because now we have to calculate CV so that we can find out which one's smaller. Okay, CV is, or CL, sorry, the lateral bracing one for the glulam is not just one. This thing is not continuously braced, and and it's braced only at 8 foot on center on the compression side. It is what we're going to have to do is use the formula from this section. So go take a look at NDS, the code 3.3.3, page 15 of the code, and just take a look at that whole section, because there's a number of formulas there. Let me look at that section real quick in my book too. Okay, so it says beam stability factor. I have a hard time with the wood code when I haven't used it in a while, because in my brain, the commentary is the right-hand column. Remember, the commentary is in the back of the NDS, and all the columns are the code when you're up in the front of the NDS. So on the right column, you've got 3.3.3 beam stability factor. We don't have any of the simple cases here. So what we need to do, if you turn the page, you'll see effective lengths. And our effective length, L sub E, we've got a single span uniformly distributed load. So we either use 2.06 times L sub U, or we use another factor. So if LU over D is less than 7, then is less than 7, then we use 2.06 L sub U. So that's the full length of ours, which in our case is this is the effective bracing, basically. This is the 8 feet on center. Okay. Our case was 8 feet over D. You check that. This is the one that controls since it's less than 7. All right. So we've got our L sub E there. What we need to find first, though, is then on the following page, on page 17, it says the slenderness ratio, and it gives you a value for that. And then it says the beam stability factor is calculated as follows. So these are all on that same section, but go to page, so this is on page 16. On page 17 are the equations that we're going to use now. So C sub L equals 1 plus the quantity F sub B E over F star B. We'll get through what all this stuff is. Over the whole thing, over 1.9 minus, and I encourage you to take this equation instead of trying to copy it from me here. Go ahead and stop the video, go to equation 3.3-6, which is what this equation is, 3.3-6 on page 17. Write it down from there. Make sure you have it right. But I'm going to go ahead and continue writing this down here. So that's that same quantity, F sub BE over F star B. My headphones keep sliding down today for some reason. Okay, sorry. So this same quantity, and this is raised to the 2, or in other words, squared, minus that same ratio over 0.95. Okay, so there's that equation. We got to figure out what these different things are. In that same section, it tells you what F sub B E is. It's F sub little b capital E for modulus, basically, equals 1.2 times E prime min prime over R sub B squared. All right, so this gets a little cumbersome in here, but this is all in that same section, and you're just trying to find each of the values. The E sub prime min, if you remember, we were talking about the E values when I went through the slides on the last lecture for this section on glue lambs. We use E sub min when we're looking at lateral stability, so that's why we use this one, and we're going to use E sub Y min, the Y min, because this lateral stability is bending weak axis. Let me just show you that. This is when, if we were in class, I would get out the white I-beam that I carry around everywhere and bend it. But essentially, if this is my beam, right? So we are bending, if I look sideways with my beam, the normal bending that we're doing is, this way, right? And we're bending about the strong axis. But when I'm talking about, so it's up and down, right? This way. When I'm talking about lateral stability, that's when it bends out of the bending plane. So that's the weak axis bending, right? Because that's the whole problem. If it's in the strong axis bending, we're in good shape. If it starts to buckle out of plane, that's when things totally change, right? It's the same as in steel class. If you haven't had steel design yet, you'll do some similar stuff to this for steel design. All right, so that's what EY value we're going to use. So EY min, this, you want to go to the supplement table 5A, EY prime min is EY min. You look up, find C sub M, C sub T, both those are 1 for our case. you look that up in the table, 850,000 psi for E, Y min. It's much smaller E value than we use when we're not in the stability piece here. So EY min is 1 times 1. All right, so it's just 850,000. We're just using this E value for this specific calculation. All right, so now back to section 3.3, in this case 0.6, equation 3.3-5 is the equation for R, capital R sub B. Okay, that's the slenderness ratio, is what this guy, R sub B, very similar to steel. You won't, if you've only had concrete design, you won't have dealt with slenderness ratios really because it's kind of an upper level topic. Most concrete, we don't have to worry about buckling out of plane. That's not a thing because the members are so heavy and stiff. But in steel you will. So R sub B slenderness ratio, similar form to the steel one, L sub E times D, which is the depth of the member, over B squared. That calculation is going to be L sub E up here somewhere, okay, is 2.06 times the 8 feet. Convert that inches to foot. D is 37.5 inches. Over 6.75 inches squared. And R sub B equals 12.8. All right, we're getting close here. So we need to verify. We should have, I just mentioned it up here, but if you wanted to make sure that we use the 2.06, it's L sub U over D, which is 8 times 12 over 37.5 equals 2.56. It's less than 7. So this is just, I just told you it worked up here, but on page 16, to use the 2.06, you have to have this true. Okay, but we could have calculated that before. Okay, so that's all good. That's, or I should put the check over here. It's fine that we use that. Now let's go in and do this calculation. F sub BE. F little b capital E is 1.2 times EY min over R sub B squared. I write that down for you over here. Yeah, so R sub B squared equals 6226 psi. So we're getting there. Oops. Sorry. I'm dropping my pages here. I apologize. And let's go ahead and calculate F sub B star, which is another one we need for that equation, which is F sub B, C sub B, C sub M, C sub T, C sub C, C sub I. All right, FB star is the reference bending design value multiplied by all applicable adjustment factors except for C sub FU, C sub V, and C sub L. Okay, so that is in the same section, in section 3.3.7. So where the equation is that we're going to use this has the definition for F star sub B. I'm going to pause here for a minute because this video is going to get long if I take it all the way to shear. So we're just going to have a pause. Go check. This is a good time to go check the different tables. Okay, and then I'm going to pick up and put a new video on, and we'll start out there with going through and doing this longer calculation to get finally C sub L.